Hey guys, hope you're doing well. We're on to our last module for this unit, module 7. So we do our research method, and hopefully we've collected a lot of data from that research. Maybe it was an experiment, maybe it was naturalistic observation, whatever it was. So now what do we do with that raw data that we've accumulated? How do we make sense of it? How do we know if that data proves or disproves our hypothesis? So that's what we're looking at today, statistical analysis. So just kind of broad overall, there's basically two types of statistics we're looking at. Descriptive statistics are taking the raw data and organizing them into some sort of useful manner. And we'll look at some examples of that in a second. And then once you have that data, a kind of whether you use mean or mode or we'll talk about, then you have inferential statistics. So now I have that data. How can I use that to draw conclusions based upon essentially my overall hypothesis? Does this prove it? Does it disprove it? What does this data mean? Okay, so we have descriptive statistics, looking at the actual data, and then inferential to infer, to figure out, okay, so what does this data mean now that I have it? And we're looking at descriptive statistics. We're usually looking at some sort of a measure of central tendency. So a measure of central tendency is like a singular, number, we'll say, that represents all of the data that we have. Okay, so if I collect, I'm doing test scores and I'm looking at percentages and I have 10 percentages, what's like a single number that I can pull out that represents all of that raw data that I have? Okay, and so these are things you should be familiar with, hopefully, for math, and we talked about them, of course, this year. But we've got mean, medium, and mode. So these are all examples of central tendency, and when you would use them, kind of just depends on your experiment. And that's something, obviously this is just like a introduction kind of to the psychology class at the college level. If you want to pursue this, especially if you want to go into research psychology, the statistical analysis in this point or something, you'll learn a whole lot more about it. Actually, so when would I use this and this and this? So the mean is the average, median is the middle, okay, and then the most often the mode is the most frequently occurring number, score, data point, whatever. Okay, so mean is the average. You take them all up, add them together, and then divide it by the number of different data points that you have. The median, just what's the middle point there, and then what number occurs the most frequently. So this for this set of numbers here. Okay, so the mode 20,000 appears more often than everything else. 25,000 is the exact middle of these 5 points, and then the mean. You add all these up, there's 5 different points, you divide it by 5, and you get 60,000. Okay, so again, hopefully this is something you're pretty familiar with. So you could use those. Another factor that you have to account for is variability. Okay, so how much do your different data points vary from each other and from the mean? Okay, and to find this, we use standard deviation, and this is that much more complicated equation that I don't anticipate. I mean, the test this year is going to be open notes essentially, so I don't anticipate you know exactly how to use it. Just kind of know what it is and what it's for. So what it does is it determines variability, how far away data points are from the mean. Okay, if it has a high standard deviation, there's a lot of variability. Okay, they're really spread out, those numbers. And if there's a low variability, they're really close together. Okay, so some examples. We have our two theoretical streets, and it says speed in miles per hour. So you have Street A, which is Perfection Boulevard. You got 35, 34, and so on. And you have Wild Street, Street B, where you have 21, and then 37, and then 50. So the mean for both of those streets is actually the same. It's 35. So the average is the same for both. So if you're like, well, what's the average speed of both these streets? It's both the same. But if you look at the standard deviation, it's a huge difference. Everyone on Perfection Boulevard is driving about the same speed. Whereas in Wild Street, they're going all the way from 21 miles an hour to 50 miles an hour. There's like a huge difference. Okay, so standard deviation predicts how far all the different data points are away from the mean. Okay, so here's the equation to get that. So you take the sum of all the deviations, square it. Okay, so to get the deviations, you have your scores, you find the mean, how far of it is away from the mean. Okay, you square it over here, so the sum of deviations squared, so that's what you put here. So 204 minus 8, or sorry, yeah, divided by 8. And then you have, these are the number of scores there, and then you do the square root of the whole thing, and 5. So it's again, a much more difficult equation to remember than just the mean, because there's multiple steps involved. But basically, the higher this number, the more variation there is. So low standard deviation tells you that the scores are pretty much all about the same, and a high standard deviation is like, wow, they're kind of all over the place. And depending on what you're looking at, that hopefully should have some sort of significance to your findings. So how can data be represented? You've got a normal bell curve, okay, which you have the mean score, and then most fall within one standard deviation, minus one standard deviation, plus one standard deviation from the mean. About 68% are in this big bell here. And then as you go far out, okay, add another one, you only got about 28% there, and then very, very little, more than 2 standard deviations out. So this is a standard bell curve. Sometimes data looks like that, or you might get a skew data distribution, okay, where you have over here a lot of data points pretty much in this area, but then like, whoa, some stuff way out here. So income per family in thousands of dollars. Most people kind of live out here, but then you have your extreme, kind of wealth all the way out here in the periphery. So an example of this, you have all these different baseball cards, the 1968, the price of them, modern day, most of them kind of about the same, but you got this huge variation of the Nolan Ryan. So if you include that Nolan Ryan card, the median is about 2.5, but the mean is 74. Without it, the median is 2.3 and the mean is 2.85. So you can have these really big outliers that massively skew your data distribution. Now, if you have most of your data, on the higher end, okay, and then you have a few notable exceptions. So we'll think about like running speed. Like this is the time in seconds it takes them to go a certain distance or whatever. Most people run about the same speed, but you have people who are really, really fast. And they can get a lot faster. So they have fewer data points out here, which skews that distribution negatively. There's a few negative outliers. Okay, so the most often is here, and the mean, because you have these outliers, is pushed over to the left. Okay, versus the positive. So positive means the distribution, there's a few outliers over here. This would be kind of like your wealth distribution like we just looked at. So most people are kind of in this area on the lower end, and there's a few super rich people that are way out here. Not that many of them, but they push the distribution way out. So you want to get your normal bell curve here, it pushed it way out over here. Okay, so negative skewed. On the negative end, there's a few extreme examples. Positive skewed, there's a few extreme examples on the positive end. Not good or bad, positive, negative, but they kind of graph positive going this way, negative going this way. Okay, it's like your x-axis. Positive goes to the right, negative goes to the left. We talked about this already a little bit. So correlation, doing a correlational study. Okay, to what degree are two variables related to one another? Okay, if there is correlation, it can be represented between numbers 0 to 1. If it falls in there, basically, that shows that the two are related. So a positive correlation would be, so there's that. I like this one better. So positive correlation will be going up, okay, up to the right. As one variable increases, so does the other variable. And if it goes up by 1, so for every dollar I give Johnny, he does 1 extra chore. That's his going rate or whatever. So it goes in a perfect line. Okay, that perfect correlation. I give him $1, he does a chore. I give him $1, he does a chore. I'm not paying my kids to do chores, by the way. This came to my head. So positive going up, and then negative going down. So as one variable increases, the other variable decreases. Okay. So as we do this one thing here, the other one goes down. Again, it's just positive and negative, just like on a graph. Okay. So this would be negative correlation. 0 means there's no correlation, it's all over the place, and 1 means that it's a perfect correlation, which does not mean that 2 factors are cause and effect. Okay, the 2 variables are cause and effect. Okay, again, super important to remember. Correlation suggests something, and it's usually worth investigating, of course, but there might be a third variable in play there. Okay, I think I talked about this example in class. As the amount of ice cream bought in the country increases, so do shark attack numbers. Okay, does that mean that sharks are attacking people who are buying ice cream? Well, probably not. There's probably a third variable there, like for instance, it's probably summertime and it's warmer outside, so people are buying more ice cream and coincidentally also spending more time in the beach, in the water, where sharks live, and giving the possibility of them being bitten by the sharks. So it's significant if you see correlation. It's like, that generally I assume it would be like some sort of result, but that you can't always say this definitely is cause and effect. Okay, sometimes it is like that, of course, sometimes it is, but not always. So these are just, smoking and depression. As smoking increases, depression increases. Does smoking lead to depression? Not necessarily. Both of those could be a sign of neuroticism, which hopefully you remember what neuroticism is from our personalities, so maybe you could review that. So as neuroticism goes up, it's one of the big ones. Okay, it's the N in ocean, neuroticism. That could be a factor increasing both of those. They are just very neurotic, so they smoke, and they are depressed. This one isn't necessarily causing this. They're both byproducts of that high neuroticism. So all this breaks down to, so you get your, you get your raw data, and then you've got to look at it. So what does this mean? Okay, your inferential statistics. Do these findings support your hypothesis? Are they giving you real data, and do they represent? So what we're trying to do is experiments by their just nature. You're not going to perform an experiment on every single person. The milligram shock experiments, like I'm not going to bring in every single person in the world to have them do this experiment to see if they'll shock their friends or whatever, or shock this poor guy who they think is being tortured. But do I have to? Can I take these people and do it? And how much does those few test subjects I did test represent all of the people? Okay, and that's where statistical significance comes in. Is it the probability that what we found, what we observed, okay, is truly because of the experiment, or is it based on other, variable things that are just due to chance? If I give, the experiment from yesterday, I give students a test at 8 o'clock in the morning, and I give students a test at 10 o'clock in the morning. How much is it like this? Those are two different groups of students, and like maybe there's some students who just happen to be smarter in one group than another group. Okay, can I say, the kids who took it at 10 o'clock, they got the better score, and that proves that having tests taken later in the day is better? Well, no, not necessarily. Those kids might just, if you especially test like a few kids, there's like some kids are just smarter in that particular later subject group. So statistical significance really important. That's why we do we do the same experiment and research methods over and over and over and over again with different groups and different groups and different groups and different groups, because we try to eliminate that chance that just random variabilities are causing these data points rather than actual showing us what we want to find out. Okay, so that's our research methods and statistics. Make sure you are doing your reading as well, looking through the book. There's ethical stuff we didn't really talk about specifically in here, but it's in the book. And then we'll have our FRQ on tomorrow, on Thursday. I'll put up there for you guys to work on. So let me know if you got any questions, and have a good day, guys.